So, good afternoon, everybody. Thank you very much for this lovely introduction. Give a talk, and I guess, like many other colleagues, I'm very unfortunate that I cannot be with you today. I hear it's a huge conference, and it would have been very interesting to talk to many of you. So yes, I now head the group at Total Energies devoted to CCUS, as we can see here. So the capture, the transport, storage of CO2, but also a little bit of its use. We're going to focus on capture today, and then maybe focus a little bit more on metal organic frameworks. So just to give you an idea of the program that I had, as was said in the introduction, around 70 full-time staff. If we include in the colleagues from academia and from industry and startups, maybe 150 to 200 people we work with. Looking at very different things, starting from the end in terms of utilization. How do we make methanol from CO2? Working with people on the X prize, again, in conversion. So this is electroconversion of CO2 into ethylene. And basic catalyst chemistry, which we will use for this CO2 to methanol pilot that we're developing. In terms of storage, all of the problems are devoted to storage, with particularly the interest in huge simulations of how we inject the CO2 and what happens to the CO2 when we injected it. In terms of transport, a lot of work on thermodynamics, how to make bigger ships if you want to transport the CO2 by ship. And then, of course, capture, working with pilot demonstration plants, different testing centers, things like process intensification. We also work with direct air capture. And then a lot of fundamental work, which is maybe quite surprising for a company working on applications. So just to give you an idea at the moment, in terms of strategy, while we're interested in CCUS worldwide, our first, let's say, playing field is Europe, because Total is a Europe. But as you will see, we have some nice strong links with China. Just to give you an idea, we have working on 2 or 3 projects here. So 3 projects here on storage. One which is Northern Lights, which will be starting very, very soon. So it's nice to have a project with both Shell, Equinor, and the support of the Norwegian government. Aramis is a project which we developed with Shell, and the Northern Endurance Partnership is a lot of companies, including many companies from the UK. But we're also looking at some of our own refineries and other refineries around Europe. So at the moment, looking very strongly in taking carbon away from the Zeeland refinery and the Normandy refinery. And just to give you some ideas, what has already started and started to be, or at least started to be planned, and in some cases have started, just to give you an idea, that CCUS is starting slowly but surely. As you know, there are very different means to capture CO2. We can have pre-combustion, where we will gasify our fuel. So this could be hydrocarbons or biomass. And then we'll form a syngas, so hydrogen and CO2, and we take away the CO2. Hydrogen is what we will use to get our power and heat. Combustion is where we will do the combustion in pure oxygen, and the separation happens afterwards, and we can recover around 80% of CO2 in the feed, if that's good. And of course, we discuss with many colleagues in different industries, for example, the cement and steel industry, and how we can work together in recovering CO2 from their industrial processes. And there are many of them. However, post-combustion is the technology that is most adapted to looking at our and working on the feeds that we have today. It's better for a retrofit, to fit after the plant is being built. If we have a new build, then maybe pre-combustion, especially oxy-combustion, can be of interest. So the rest of my talk will be mostly devoted to post-combustion, but I would like to show you just one thing that we're doing in terms of oxy. As I said earlier, Oxycombustion, you recover the air, and often we have air separation. This air separation unit is quite expensive. So what we're developing, and we're developing this with a European Chinese project called CHEERS, is what we call chemical looping combustion. Here we have a first reactor, which is charged at the moment often with an oxide. And this oxide will change the valence to have more oxygen in the oxide. This is transferred then into the combustion reactor, where the oxide heated releases pure oxygen, and we can have the combustion here. The advantage is that we get energy, and we think that it's cheaper than using an air separation unit. So what we're doing with our project in China is building the demonstration unit in China, and then hopefully we're discussing to find out how we can move this on to demonstration level. So working with both our Chinese colleagues, but also with other colleagues around the world. But you can see that our work here is very much carried out with Tsinghua University. So just to say that we're also working in other areas, and very happy to work with people in China, of course. If we come back to post-combustion, maybe the easiest and first thing to do is to go to testing centers. And we work with 2 testing centers, one in Norway called TCM, and then one in Texas called the National Carbon. And here what we can do is follow startups, but also some large companies in testing their solvents, and compare the solvents to newer technologies, for example, adsorption. Largest. If we do have adsorption down here at the bottom, we do have to compare adsorption with cryogenic separations, with, of course, absorption technology, which is standard, membranes, but also emerging technologies, for example, molten carbonate fuel cells, with only one company that I'm aware of, which is based in the US, and has had money injected from ExxonMobil. We think adsorption is interesting because of the low energy needed for the separation. It's a mature technology, but we have to work on things like selectivity, capacity, and sometimes for the cases that we have today, for example, with Air Liquide, the gas pretreatment is something we would like to work on. And of course, the footprint it takes on the ground. The other thing we can think of is combining cryogenic capture with adsorption, or cryogenic capture with membranes, for example. That is something we're also looking at. We focus now a little bit more on adsorption, different ways to carry out this adsorption. Of course, we know about fixed bed adsorption, where we have a bed and we have the solid adsorbent inside. This approach is interesting because they actually try and carry out the adsorption at the temperature of the flue gas, so no cooling, so at around 100 to 120 degrees. A hybrid system, also from TDA, membrane plus adsorption. Interested in looking at fluidized beds, falling beds. This is also like a fluidized system with a heat pump in the middle. But if we're looking to laboratory scale technologies, looking at things like hollow fibers, we think of interest, because this is quite a short cycle, so a 3-minute cycle, which is very interesting. Another very short cycle is a rotating bed, and I'll come back to our work with a company called Svante, which is a Canadian company. This is a rotating bed system, very much of interest. I guess that many of you know what adsorption is. Many of us work with new materials, adsorbent materials, but these have to be put into contact with the CO2. So not often in terms of beads, but we can think of solid materials like this, or we can think of hollow fibers like this, where we have maybe the cooling water inside the hollow fiber and the adsorption just happening on the outside, for example. So the contact with the CO2 is very, very interesting. And then, of course, the adsorbent and the contactor is put into a process. And of course, we know about temperature swing adsorption, we know about pressure swing adsorption, and we know that pressure swing adsorption is well used around the world. And this is a PSA plant in Leine in Germany. How do we compare metal organic frameworks with other materials? The comparison is we can carry out on many levels. It can be in terms of stability, price. We can also just work on order, for example, and or size with respect to order. So, of course, we know that zeolites are very, very nice, mostly nice ordered porous materials in the micropore, slightly into the mesopore range. Very, very stable. Very well known, very well characterized, and excellent materials. MOFs give us some of the advantages of zeolites in terms of stability, in terms of flexibility and order. A little bit more flexible than zeolites. We know that zeolite row is flexible, for example, but the flexibility of MOFs is on another scale. And then we can compare maybe these two very well ordered materials to things like clays, periodic mesoporous oxides, templated carbons, a similar family, and then less ordered materials, things like silicas and, of course, active carbons. Active carbons, of course, being very stable and very, very water stable. To compare our different families of porous materials to MOFs, we have this huge variety of structures and chemistries with many thousands of catalog structures. Very much, if you look at the image at the top, is very much like a slot machine. When you're playing slot machines, you have these different numbers coming up. You have a different metal cluster, a different organic linker, and we can make. The challenge here is to find out what is the best structure, but also what is the best linker, what is the best chemistry, what is the best functionalization. So it's almost an infinite variety of materials. And I think this is one of the big challenges, is finding the right material for the right application. And then, of course, there's a growing number of MOF vendors, and I've just picked 3 or 4 here. But of course, there are many large number of MOF vendors. The question is, how do we find this optimal material? So we can turn to databases with hypothetical known materials, so that we know about the MOF core database from Georgia. We can screen these databases for specific from Berit Schmidt and Tom Wu did in 2019, found that this was the nice absorption site with 2 parallel benzene rings. The CO2 could go in there, water not so much. And then they looked at different types of materials that have these types of structures from a very, very wide range of materials to study. The other way is to look at the process optimization, and we can link this to, for example, different types of process screening, so different types of steps. How can we optimize these different steps, for example, with different screening metrics, also the use of machine learning. With an idea in terms of process screening of taking, for example, this is for zeolites, taking over 120,000 different lights and other porous materials, and then screening for parasitic energy, and then taking the top 5 lights or and optimize to find out what standard, which is still 30. A lot of this work that we follow is with the University of Alberta, for example, but there are again many groups around the world that are looking at this process optimization. So what it then should be of interest is to combine this pure materials optimization that we have here with this process optimization that we have here. And if we can link these two together, then maybe we can have a tool that is very, very powerful. But having said that, we have to take into account the realities of applications. And the realities of applications are things like we may have a nice structure, but when we make it, it can be interpenetrated, for example. We may have to think about stability. Stability for John Lowe. And of course, we can think about costs. The cost of materials, We choose in terms of MOFs, we have to find the materials with maybe the cheapest linkers and some of the cheapest oxide materials, and then still worry about interpenetration and stability. These things we're looking at. I'd like to say in terms of research, this is something we should not worry about too much to start with, because if we find a nice material, we can have confidence in our chemists if we take this nice material in trying to make it cheaper, maybe changing the metal for something else, for example. Of course, following MOF stability is of interest, and these are water adsorption on different types of MOFs. And we can see here for this material, very, very stable, very well cycled over 6 cycles. You can see exactly the same isotherm here. The UAO66 materials are water. Maybe at the very start for the first step, a little bit of rehydroxylation, but it's good. And of course, we know of many materials which are not stable. And these things we have to be able to identify as quick as possible. And I think it would be good to have a screening methodology using molecular modeling to be able to screen out some of these materials. So something we did when I was still in Marseille was take a series of different metal organic frameworks, add them to zeolites, here's 13X, also to inactive carbons, we have 1 and 2 active carbons, and we ranked them. How did we rank them? We carried out the CO2 adsorption in a thermogravimetric apparatus, so the CO2 would uptake. We did this on a dry sample, but we also subjected the materials to water. And so we allowed the water to stabilize with the material. And then we carried out the CO2 in the presence of humidity, which was adsorbed inside the material. And we can see here, we made a ranking of those which had a little effect, medium to strong effect, and then quite a strong effect on CO2. And we can see here, of course, that we know that in many cases, zeolites, water absorbs preferentially with respect to CO2, and we can see that our 13X is down in this last category of materials. We also can see that active carbon is, many carbons are fairly hydrophobic, and so if they're put into the presence of water, maybe only a small amount of water is absorbed, and so there's little effect. But what we can see is some materials in this category here and this category here could be of interest. And if we just look at the blue lines, so the CO2 adsorption with the MOF that's already been impregnated, which is wet, we can see we have that this material here seems to be of interest under our study, so MIL96. But also this material, these ones here, but also this material, MIL127 or SOCMOF. What we can do here is find a way to compare a CO2 capacity loss here, so the difference between the orange line and the blue line, and then we just compared it with the strength of interaction of water with our material. In most cases, we'll have a straight line because the water takes the same sites that the CO2 would like, and there's potential absorption of water. There are some outliers. MIL53 we think is an outlier because it's a flexible material, and it's a flexible material in the wrong direction for us. But these two outliers, MIL96 and MIL127, which I talked about here, so the MIL196 here and the MIL127 over here, do seem of interest. And it's worth looking at these materials a little bit closer. This is what we've done here. So this is MIL127 material. So if you carry out the adsorption over various cycles, so for the dry sample, we have the adsorption over a little bit, 5 milligrams of CO2 per gram. We have an increase as we increase the number of cycles. And this is in the case where we have pre-equilibrated in 40% water. So there's 40% water pre-equilibrated in the system, so quite a lot of water. But we still see an increase in CO2 adsorption. If we go to higher water amounts, then we start to see again a decrease in the CO2. But still, an interesting result. What we can then do is look at the energies. We can see here that the energies decrease over various cycles. what we think is that the CO2 after the first cycle is able to push out some of the water. There's still some of water available, and we can see that we have, as we do the adsorption and the desorption, water reabsorbs during the desorption, but the CO2 pushes. And this balance between the heat of adsorption and the heat of desorption gives us this low enthalpy here, these low energies here. And we can think of this as, we talk about intrinsic, so internal heat management, but it's very much a play between water and CO2. And this is, I think, a one way forward. Of course, we have to think about other contaminants such as NOx and salts. So, as was said in the very lovely introduction, I'm very much interested in fundamental phenomena. And if we have to think in the long term, one of the things we have to do is decrease the energy used for the desorption part of our system. And so if we do look at the long term, we have to think of look at the results at the lab scale. I think photo switchable MOFs are quite interesting. This is some work carried out almost 10 years ago where they looked at the effect of UV, and after 5 hours of UV, the people suggested that we could have different conformations of the linker here, and the linker could be more or less open to have more or less space for the CO2. More recent results are not with CO2, but again, these gate opening and gate closing effects here. And this is carried out in the liquid phase with this pyrene carboxylic acid. But I think it's very interesting to see these different types of materials and these types of opening and closing. So I think quite nice. The other thing that I think is nice here is that they looked at core shell MOFs. And this again is something that could be of interest if we can make them at a large scale. So light-assisted desorption is something carried out in Australia. Matt Hill's lab is one of the groups looking at this. In looking at it, so again, this is CO2 uptake, and they've turned the light on, they've turned the light off, and you can see this light on and the uptake with the light off Here they've used silver as the material that will interact with the light. Of course, the problem here is that if we're looking to the process side of things, is how far does the light go into the material, into the film, for example. So this may be worth looking at in terms of films, maybe in interest for things like sensors. Still, interesting to see this light-assisted absorption. Again, if it is light, then it's very energy efficient. Think of magnetic frameworks as well, and I think this is something of interest. Again, this is from Matthew Hill's group. And what they did is they took a large pore, or quite large pore MOF, this MOF 74, and they put in iron oxide. So the iron oxide inside the pores, this magnetite interacts with a magnetic field, and we can get magnetic heating. Again, of interest because a magnetic field is an electric source, is a source of energy which is from electricity, which could in the future be renewables, for example, and uses much less energy than we would use using a conventional steam, for example. So a nice, interesting way forward in terms of an interesting result. I very much like this trapdoor mechanism. So this is coming back to zeolites. Some of the initial work, Jin Shang, who I think is now in Hong Kong, was working in Australia with his molecular trapdoor shabazites, in which he showed that CO2 could enter some of these materials and not methane and also not nitrogen. He also showed that there was an effective temperature, but very nice work. And this has sparked much other work, and I very much like this publication, which is from this year. And we can see here that there's the sodium sapo rho zeolite, so this time a rho zeolite and not the shabazite. And we can see that the sodium zeolite gives this nice separation factor here. Yeah, so very much of interest. But what we do think now, and again, this is coming back to the use of molecular modeling, is that these molecular insights into what we call a trapdoor mechanism may be more a swinging door mechanism. which is a result of the thermal activation of the cations inside. So the temperature of the adsorption is of importance. And this could be something of interest when we are looking to coming back to the process. Can we play with a subtle difference in temperature to have this swinging door or trapdoor mechanism in play for different types of separations, but including the CO2 separation from nitrogen or from methane, as we're seeing. So I think these trapdoor mechanisms are a way forward to start to look at zeolites. Again, it would be interesting to look at the effect of water on this, because water is in our flue gas streams often. So coming back to some ways forward for MOFs in research, from an industrial point of view, we are looking at lowering the regeneration energy. So I've talked about magnetic induction, light induction, also things like microwave desorption. Quite simply because these are electric, using electricity, and this electricity is renewable. If we're looking forward to the carbon footprint of our process. At the start, I talked about a computational screening, either data-driven design or this batch absorber analog technique, which is just looking at the process. What we can see here is that they calculated the thermodynamic separation limit, and we can see that we are quite a far away from this. So one of the ways forward is to try and find materials using maybe this type of technology, this type of approach, to come down to the separation limit. And then flexibility. So I've put the trapdoor mechanism in sort of like a flexibility type mechanism. There are two works which aren't devoted to CO2, but this is methane storage in a MOF from Jeffrey Long's group, where we can see that in terms of the enthalpy of adsorption as a function of methane loading, there's a huge decrease here. And this corresponds to a big step in the CO2 capture rate. And this is because the system is very, 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 very flexible. But also things like ZIF8, we know that there's some sort of flexibility there. And we can think of maybe a stiffening or a non-stiffening of the structure, depending on the process and on the parameters that we used. Again, very, very lovely work. So this is maybe a way forward to think of new ways for separations. The question behind this is: these new separations, can be made to an industrial scale or not? But I believe that our industrial large-scale emissions we should work on now, but maybe we'll have smaller scale emissions in the future. For example, if we're using, for example, bioenergy approaches, these may be smaller plants. But of course, bioenergy, if we add capture behind, and the source of bioenergy is from waste organics or waste agricultural, then we can have a negative emission technology. And that is something I think in terms of research that we should work on, and we are working in our groups. Okay, so we've seen all these different MOFs, we've seen all of these different approaches, and we've stayed at the laboratory scale for the moment. Let's move up a scale. We'll go to the pilot scale. So we have been lucky to work with this Canadian startup company called Svante. And if we come back to these, my 3 points here, they have a process which is a temperature swing process working on variations of temperature. It's basically a 4-step process: catching, releasing the CO2, and then drying the system and cooling afterwards. So this is what they're doing, a 4-step process. And this cycle is of interest because it takes 1 minute. And this is an idea of what would happen on the full scale. So a temperature swing process carried out under 1 minute. So this is of interest for if we want to have compact systems, but also of interest for full scale, because we can have 3 or 4 of these next to each other, and they take up the same footprint as an amine scrubbing unit, for example. What is of interest here? Why can they go so fast? Quite simply because they have this contactor, which is a laminated contactor, and the CO2 comes through these laminates. And they make sure that the laminates are just the right size that there's a full contact of the flue gas as they go through this bed, which is about 1 meter high, 1.2 meter high. And they use an adsorbent material, which is on these laminators. So the adsorbent material that they've been looking initially were amine functionalized silicas. But amine functionalized silicas don't give us this nice cycle. There are one or two problems with this cycle, this amine functionalized silicas. But there are metal organic frameworks that they've been looking at. You can see this functionalized MOF74 type structure. This is one of but this material here is called CAF20. You can see very, very simple material developed by George Shimizu. And this material is making a difference and is being tested at the moment on this large scale. So what have we been doing? We've basically, there are two ways forward. We could either buy into the company and push them forward, or we can leave them to be agile. It's a small start. We just help them forward with some ideas or some testing. So we've been working at new materials with different universities. This is a small demonstration unit, and the cycle is here, this first part here. And this demonstration unit is in one of our laboratories, not far from where I am in the southwest of France. And we look at this cycle. We test the materials that are sent to us. And we've been carrying out cycles now for over 4,000 hours on one of their materials. So this process demonstration unit is a way forward to go to higher scale. So this is 0.1 tons of CO2 per day captured, 1 ton, 30 tons. And at the moment, looking at a full-scale demonstration on a cement plant to see whether this type of process could be of interest for capturing flue gas from cement. So you can see that this is a full-scale system, around 1 million tons per year. So you can see both that we're helping the startup ourselves directly, but also working with colleagues from other industries to try and de-risk together a technology. And this demonstration could be on their plant or on one of ours. Oh, I have a few minutes to give you some final words. What I wanted to hopefully show you is that we are starting deployments. Indeed, initially centered around Europe, quite simply because there are a lot of funds in Norway, a lot of funds in the Netherlands, quite a lot of funds in the UK and in Belgium to start this deployment, and so that the governments are pushing us forward. We're also seeing that other places around the world, in the United States, government has changed, and they're also pushing this forward, and we hopefully to hopefully be able to work there. And certainly, I believe that there are opportunities in China, and our office in China is very interested to understand, and they do follow what is happening there. So I think very, very, very much of interest to start deployment where the government wants to. Well, I've just talked about new contactors. So this sheet contactor and new processes. So this is a demonstration scale, the smelting process. So this demonstration scale is 15 meters wide. Robust technology is just basically a heat exchanger with a fluid inside. So looking at these types of processes, but of course looking at other processes from other startups. And I just gave you one example. Linked with this, we can start to think of whether we can use these type of contactors with materials which give us new phenomena. So we've talked about this trapdoor mechanism, which I think is really interesting. We're also very much wondering whether these types of processes, these rapid processes, can be linked to some sort of electrification. So this process uses steam for the moment, but maybe we think that we can reduce the amount of steam and maybe have more electrical regeneration. And then, of course, we can think of new materials in terms of screening. But also, one of my pet hobbies is to look at new phenomena and understand these new phenomena. And here we're building up on the computational scale, new materials. So these are standard materials, but looking at the effect of how this material would be inside when it's shaped inside the contactor. So the material here, the MOF here, is painted onto the structure. and we have to worry about the effect of the glue here. So this is the idea of looking at the flow of CO2, water, which is blocked on the surface, and nitrogen, and how that flows through the system. So fundamental understanding is very much linked to what we think can happen in terms of process. And we need all of this range of understanding. So hopefully, as we move forward, maybe some of these processes can be moved into some of these deployments further going. So coming towards the end of my talk, I like to finish with a saying, so I've just taken this one. I very much think that the work that we're doing has to be done with other people. So the fundamental level with academics, we need to understand the different phenomena, and we need to be able to think about different materials, and we need to have a wide view, and we need to keep our eyes very much open. So we need to bring the community together. In some of the work that we're doing, we're working with other groups, looking with either universities, but other startups, and also other large companies, other oil and gas, petrol companies. So coming together, at least for the carbon capture area, is very important. It is a beginning. And we need to work together in the future if we want to try and recover this CO2 and store it permanently. So we need to stay together in some of these, in many of these programs. And of course, working together is going to be the success of what we're doing. So I think I've come to the end of my time, and I'd very much thank you all for your attention. It's been an honor and a pleasure to talk to you.